Welcome back to the channel. In this lesson, we'll start our series of lessons on electrostatics. I'll start with Coulomb's law of electrostatics. I will explain the formula that relates force with each of the charges, and at the end of the day, we'll use a work example to help you understand it better. That said, let's get into class. Like I promised at the introduction, I said I will explain Coulomb's law of electrostatics. Now, there are two laws of electrostatics, the first law and the second law. The first law of electrostatics tells us that like charge of electricity will repel each other, whereas unlike charges will attract each other. That is, if I have two charges this way, I have Q1 and I have Q2. If Q2 is positive and Q1 is positive and Q2 is positive, Coulomb's law states that these two charges are like charges and they will repel each other. They will move in different directions. If Q1 is positive and Q2 is negative, Coulomb's law tells us that these two forces will attract each other. That is, they will attract each other. The second law now tells us about the strength of the force of either attraction or repulsion that exists between these two forces. Let's see it. Now, Coulomb's second law tells us that these two forces, whether it is attraction or it is repulsion, Coulomb's law tells us that this force is directly proportional to the product of their charges. That is, my force that exists between these two charges, force F here, F will be directly proportional to the product of their charges, Q1 times Q2. At the same time, Coulomb's law also says that this same force F will be inversely proportional to the square of the distance between them. That is, F now is inversely proportional to the square of D. Now, if you can put these two together, you will know that F now will be proportional to Q1 Q2 over D square. So because we're talking of proportionality, there is a constant of proportionality. So that we're now saying that F obviously will be the same thing as K, which is my constant of proportionality, times Q1 Q2 over D square. Now, K itself, the constant of proportionality, is actually a function of the permittivity of the medium. Now, between these two charges, Q1 and Q2, there's a distance between them. Obviously, if there's a distance between them, there's a medium between them. That medium could be air, that medium could be any form of material. Now, the characteristics of this medium will affect this force, and that is where K now comes in to tell us of its relationship with the permittivity of that medium. So that K now is said to be equals to 1 over 4 pi the permittivity of the medium. Now, the permittivity of the medium also is divided into two. The permittivity is divided into two, that is, the absolute permittivity, which is denoted as E naught, and the relative permittivity, which is denoted as ER. So that we say that E now, the permittivity of the system, is the product of the absolute permittivity and ER. So that K on its own is the same thing as 1 over 4 pi ER E naught. We also know that E naught, or the absolute permittivity if the medium is free space, relative permittivity ER of free space is 1, while the absolute permittivity of free space is the same thing as 8.85 times 10 raised to power minus 12. Now, E naught is given as F over M. And so that E naught now, so that K now will be the same thing as 1 all over 4 times pi times 8.85 times 10 raised to power minus 12. So that K now will have a value of 9 times 10 raised to power 9 if you use your calculator when we are dealing with free space. But when we are not dealing with free space, the permittivity or the absolute permittivity of that material will be different. Let's take an example. My question says we should calculate the electrostatic force of repulsion between two A particles when at a distance of 10 raised to power minus 13 meters from each other, and charge of each particle is given as 3.2, that is, Q is given as 3.2 times 10 raised to power minus 19 coulombs, and Q2 also is given as 3.2 times 10 raised to power minus 19 coulomb. The distance d between them has been given to be 10 raised to power minus 13 meters. Now, since we are not told of the part of the kind of material it is, we'll assume it's free space, so that our K in this instance will be the same thing as 9 times 10 raised to power 9. Now, my F, remember, is the same thing as K times Q1 times Q2 over d squared. So that my F now will be the same thing as 9 times 10 raised to power 9 times Q1 3.2 times 10 raised to power minus 19 times 3.2 times 10 raised to power minus 19 over d squared. My d is the same thing as 10 raised to power minus 13 all squared. So that F now will be the same thing as 9 times 3.2 times 3.2, I'm just rearranging, times 10 raised to power 9 from indices, my minus 19, this becomes minus 19, minus 19. I have 10 raised to power minus 20, minus 13 all squared. This is something as 2 times 13, that's 26. Since I have the 13 is dividing, it comes up here to become plus 26. So that F now will be the same thing as 9 from my calculator. I have 9 times 3.2 times 3.2, that's equals to 92. That will be 92.16 times 10 raised to power. Now let's get the indices. That's 9 minus 19 minus 19 plus 26. That's minus 3. That's 10 raised to power minus 3 Newton. Minus 3 Newton. With this, I hope you understand how to simply calculate the force of either attraction or repulsion between two charges. In our next lesson, we'll continue with electrostatics. Thank you for staying with us and see you in our next class.